It's a tradition on October 31st that Mr. Roosh takes the day off and I, Captain Derivative, his alter ego, replace him. So I hope you can put up with me today. It is getting near the end of the Calculus 2 course, so just a little bit of a peek ahead to Calculus 3, which I hope a lot of you will take, where in parametrics we have a position of a particle moving along some kind of curve represented every point by x of time t and y of time t. Well, that can really easily be put into a vector. In Calculus 3, you start talking about the calculus of vectors. So you could have a vector coming from the origin, and that vector could be called r of t. And that could be x of t, y of t. Or, if you like, x of t I plus y of t j. Just kind of letting you know what might come in the future. And associated with this position vector is also a velocity vector, which has as its components what we've been talking about, x prime of t, or dx dt, and y prime of t, and there's even an acceleration vector, which is x double prime of t, y double prime of t. So these would tell some things, like the velocity vector turns out to look like this. So this is something that has great value when you're talking about positions of particles moving and wanting to know how their movement is changing. And I think you can see the great advantage to parametrics is this would be really easy to change to a three-dimensional path. All you would have to do is add a z-axis out here, and all you'd have to do is add a third component, z of t, into the vector. So it's not really a big transition. Anyway, I thought we would end up parametrics today with a few examples. Well, here's one. At time t greater than or equal to 0, a body moves along a curve in the xy plane, and you have its velocity vector. Well, I don't even have to mention vectors as long as you know what this is. You know that if this is the velocity vector, basically x prime of t, or dx dt, is t to the 1/2, and y prime of t is t squared. So we're kind of starting off where we often do, where we know something either about x of t and y of t or about their derivatives. And we do know one thing about the position. We don't know the position x of t or y of t, but we do know that x of 4 is 2 and y of 4 is 3. So we know one position at time 4, whatever the path happens to be, the particle, or the body in this case, is at position 2, 3. So the first thing wants to find the position of the body when the speed is 2. So we have to think, what is speed? Speed is the square root of dx dt squared plus dy dt squared. So we already know dx dt and dy dt. So in this case, it's the square root of the square root of t squared plus t squared squared, or the square root of t plus t to the 4th. So that's the speed any time t, and we want to know when this is the square root of 2. Well, just by inspection, you can see that that happens at t equals 1. There will be another place when t is negative, but we're talking about t greater than or equal to 0. So now we found the time. We still have to find the position at that time. So what do we know? We know the position at time 4, and we're trying to find the position at time 1. So we know that x of 4 is x of 1 plus how much the x variable changes between 1 and 4. Well, that's going to be the integral from 1 to 4 of x prime of t dt. So from this, you can see that x of 1 is the position at time 4, which we know is 3, minus this integral from 1 to 4. And x prime of t is t to the 1/2 dt. And the same thing we can do with y. Y of 4 is y of 1 plus the integral from 1 to 4 of y prime of t, or dy dt. So that means y of 4 would be 2 minus the integral from 1 to 4, and y prime of t is t squared dt. So that means, let's do these integrals. The integral from 1 to 4, well, we can just do it. It's the antiderivative is t to the 3/2 times 2/3 from 1 to 4. So we get 2/3 times 8 minus 1, or 14/3. And the integral on this side from the antiderivative of t squared is t cubed over 3 from 1 to 4. So you get 64/3 minus 1/3, or 63/3, or 21. So that means these are the changes in position. So when the x started out, well, if we go 3 minus 14/3, we go minus 8/3. So that would be the x-coordinate at time 1, and the other one would be 2 minus 21. Or, oh, I think I did that wrong. I think the y-coordinate was 3, and the x-coordinate was 2. So this would be 2 minus 14/3, which is minus 8/3, but this is 3 minus 21, or negative 18. So that's where the particle was at time 1. This is where it is at time 4. Okay. Find there's a place on the curve where the slope is the square root of 27. So it gets really steep at some point, and we want to find the time. So we know the slope, dy dx, is dy dt over dx dt, or y prime of t over x prime of t. And y prime of t is t squared, and x prime of t is t to the 1/2. So altogether you get t to the 3/2. And if I want to know the time that equals 27, it's just 27 to the 2/3 power, or at t equals 9. So we know the position at time 1, we know the position at time 4, and somehow this path starts getting pretty steep because the slope is 27 by the time you get to time 9. Now, as far as the acceleration vector is concerned, we haven't talked about the acceleration vector, but it's not a big deal. All you have to do is take the derivative. So a of t, you're going to get by taking the derivative of x prime of t. So you get 1/2 t to the negative 1/2, and y double prime of t would just be 2t. So if you want to know it at 16, it's just going to be 1/8, and then 32. So that would be your acceleration vector. Okay, well, instead of a body, this time we have an ant who starts at point A at time 0 and travels to B and then to C and then to D, and it gets here at time 9. The ant's position during the trip is given by x of t, y of t, because this is in the xy coordinate system. We don't know those, but they're both differentiable functions, but we do know x prime of t. Unfortunately, we don't know y prime of t. Let's see what we can find out of this. It says, at point C, find the signs of dx dt and dy dt. On this, we don't have to do any calculation. We know the path is going like this and coming down like this. So at C, as time is getting bigger, both x and y are getting smaller. It's moving to the left and down. So we know that both of these are going to be negative. B, the slope of the curve at point B is undefined. It kind of looks that way. It looks like if you touched it, it would really hurt your hand. So, what do we want to do? We want to find the time the ant is at point B. Well, what is going to make an undefined slope? Slope is dy dx, which is dy dt over dx dt. So to make it undefined, dx dt must equal 0. And we've got dx dt right here. So what is the first time that that's going to be 0? Well, we know the sign of pi is 0. So when t equals 3, this will become the sign of pi. The next time would be at 2 pi, but that won't be until this is time 15, that you would get another time where that equals 0. The cosine of pi over 2, and that's also at time 3. So at time 3, both of these factors are 0. So all you really have to do is say, right here, that must be at time 3 that you're up at that point. So we haven't had to do too much calculation yet, just a little bit of thinking about what these things mean. Now, at time 8, the line tangent to the curve has the equation y equals 5/9 x minus 2. So maybe that's time 9, so maybe at time 8. Right there we know the tangent line. Find the velocity and vector and the speed at that time. So we need to find dx dt and dy dt at time 8. Well, x prime of 8 we can get just by plugging into here. We get negative 9 times the cosine of 4 pi over 3. That's negative 1/2 times the sine of 3 pi over 2, which is negative 1. So it looks like it's a negative 9/2. So now we can do part of the velocity vector. We know x prime of 8 is negative 9/2. But we do need to find y prime of 8, and we don't have y prime of t. But we do know that dy dx is dy dt over dx dt. And so we know dy dx right here is 5/9 because that's the tangent line. So that has to equal dy dt over dx dt. And dx dt is negative 9/2. So that must mean that dy dt equals 5/9 times negative 9/2. You get negative 5/2. And there's your velocity vector. And then to get the speed is just the square root of dx dt squared plus dy dt squared. So it would be negative 9/2 squared plus negative 5/2 squared. And you could get a number if you wanted to on your calculator. And the last thing asked, how far apart are A and D? Well, if we think about it, you're just looking at what's the change in the x coordinate. And we know how to do that. If you take the integral from 0 to 9 of dx dt, or x prime of t dt, that's going to give you the change in the x coordinate. So it's just going to be the integral from 0 to 9, and we know what dx dt is. Minus 9 cosine of pi over t for pi t over 6 sine of pi times the square root of t plus 1 over 2 dt. Now this is something you probably want to use your calculator on. And it's something I haven't focused on a lot this year, but it's really easy. Once you understand calculus, all you have to do is push a button and all of a sudden the integral sign shows up and you put in the function and you get an answer. And I think this turns out to be somewhere around 39, but it comes out to be negative. And you say, oh, did I do something wrong? And you have to say no, because the change in position was actually, x is getting smaller and going from here to here. So you would expect the change in position would be negative. So to actually answer how far apart they are, you would have to take the absolute value of that. So you come out to be somewhere around 39.2, I think. So, let's go to one more problem. A spotlight shines on Cubic Island. So this green is a portion of Cubic Island and is rotating at 180 degrees per minute. And it's doing it counterclockwise. So you have the spotlight at the origin that's rotating counterclockwise, and its light is shining on point P, but point P will be moving as the spotlight moves around that point P along Cubic Island will be moving along the shoreline. And it moves from 1/8 or 1/2 1/8 to 3/27. And we know that the shoreline is y equals x cubed, at least at that portion of the island. So the key is, how fast is point P moving along the shoreline when you get to the point 1, 1? So this is where, you're coming to the end of a calculus course and you're thinking, I've got to use all the things that I have in my head. Well, what's the only thing that we have that says something about the movement of a particle along a curved line, about the speed of it? How fast is it moving? Well, the only thing we know is speed is the square root of dx dt squared plus dy dt squared. So that means I somehow have to figure out what dx dt and dy dt are. And those are both rates of change. And I see the only rate of change I have is right up here. And that's what? That's the rate at which the angle is changing on this spotlight. So somehow I have to relate dx dt and dy dt to d theta dt, where theta is the angle that this is making. So if I call this theta, and since this point right here in the xy coordinate system, you could call xy, you have a right triangle. And this is x, and this is y, and this is theta. And that we know theta is changing at that, so I can write d theta dt is 180 degrees per minute. But knowing that we're working in calculus, we know we have to use radians and not degrees. So 180 degrees is pi radians. So this is pi radians per minute. So what's the relationship that we have? Well, if we want to use theta and the opposite and the adjacent, we're going to use the tangent. So we say the tangent of theta is y over x. But we're trying to find both of these. We can only have one unknown rate. This is a related rate problem. So even though we're in parametrics, this turns out to be related rate. But what do we know? Since this is along the shoreline, we know that it's on the curve y equals x cubed. So really, it turns out to be tangent of theta is x squared. So now what do you do in a related rate problem? You take the derivative with respect to time. So we get secant squared of theta times d theta dt equals 2x times dx dt. And we're trying to find dx dt. Well, when you're at the point 1, 1, when y is 1 and x is 1, we know that's going to be the square root of 2. So the secant of theta is going to be the square root of 2 over 1. And d theta dt is pi, and x at the point 1, 1 is 1. So we get 2 pi equals 2 dx dt. So dx dt is just pi. But we still need to know dy dt. But what do we know? We know that y equals x cubed. So dy dt is 3x squared times dx dt. And x is equal to 1, and dx dt is equal to pi. So now we know dy dt is 3 pi, dx dt is pi. We can go back and answer our question. The speed is going to be the square root of pi squared plus 3 pi squared or the square root of 10 pi. So kind of a fun problem. And it gets back into what we learned in Calc 1 about related rate problems, and using the latest thing we've learned about parametric equations. So that pretty much finishes up parametric. And I think you're going to find that really there isn't that much you need to know how to do. So basically, a quick summary. Oftentimes you're given x as a function of t or y as a function of t. And most of the things that are really helpful are dx dt and dy dt, because all these give you are positions along the path. If you take the derivative of these, then we're finding the rate of change of x and the rate of change of y, both with respect to t. So certain things we can find. When dx dt is positive, it means the particle is moving to the right. When dy dt is positive, it means y is getting bigger as t is getting bigger, so you're moving up. And we know other things, that if you want to go from at t1 at some position to t2 at another position, you can just take the original position in x plus the rate of change of x times the time. We did this on a problem just earlier. And the same thing with your y value. You can find the new y value from the old y value plus the change in the y value. Also, we can find the speed at any time. Basically, the speed is putting the rate of change in the x direction and the rate of change in the y direction together and adding them up in the proper way. And if you know the speed, you can find the length along the curve from one time period to the other by taking the length is equal to the speed times the time, from this time to this time. And the last thing is the slope along the curve. Using the chain rule, we proved that the slope, dy dx, is equal to dy dt over dx dt. So once you've found dx dt and dy dt, it's pretty easy to get the slope. Now what's a little bit harder is to get the concavity. But we have to realize once you take dy dx, you're going to get another function here, which is a function of t. So if you want to take the second derivative of dy dx, take the derivative of dy dx, which gives the second derivative. What we're having to do is take the derivative of this new function of y with respect to x. So we have to use the same formula, but now we take the derivative of this new y with respect to t, and x itself is not changed, so it's the same dx dt. So that's maybe one of the most complicated things in parametrics. I did show you some things about how to find areas and volumes of revolution and surfaces of that volumes of revolution, but really that's not the most important use of parametrics. It's really movement along lines that are going to be the best use of parametrics. So anyway, that takes care of parametrics. In our next talk, Mr. Roosh will be back, and we'll talk about a new way of representing things in the XY plane.